At 7:15 on the morning of November 14th, 1963, the cook aboard an Icelandic fishing trawler saw a column of dark smoke rising from the open sea. The captain turned the vessel toward it. Their first thought was simple. Another ship was burning. But there had been no distress call, and as they moved closer, the ocean itself began to explode. Black ash, steam, and fragments of volcanic rock were being thrown out of water that had been empty only hours before. Beneath the crew, magma had risen from a fissure roughly 130 meters below the surface. By the following day, the chart was already wrong. A new island stood where there had only been sea. Today, almost no one is allowed to set foot there, because a single contaminated boot could damage one of the longest-running natural experiments on Earth. This is Surtsey. To understand why this island is closed, we have to return to the moment before it existed. Surtsey lies south of Iceland, at the far end of the Westman Islands. This is a landscape built by the Mid-Atlantic Ridge, where tectonic plates are slowly pulling apart and magma repeatedly finds a path toward the surface. But in November 1963, that path was hidden beneath the Atlantic. The eruption probably began on the seabed before anyone saw it. At that depth, the weight of the water initially suppressed the violence. Magma could cool, fragment, and collect without breaking the surface. Then the growing volcanic mound entered shallower water. The pressure dropped. Seawater reached magma hot enough to turn it into steam almost instantly. The expanding steam shattered the magma into ash and drove black explosions through the ocean surface. This was not lava calmly building land. It was a contest between construction and destruction. Every explosion added material. Every wave carried some of it away. Yet the volcano was producing ash faster than the Atlantic could remove it. On November 15th, a ridge of black tephra stood above the waves. Over the following weeks, the ridge became an island. By the end of January 1964, its highest point had reached roughly 174 meters above sea level, more than 300 meters above the seabed, where the eruption had begun. The activity shifted between vents. New submarine eruptions produced temporary neighbors named Surtlingur and Jolnir. Both were later erased by the sea. Surtsey survived because its story changed. When lava began flowing across parts of the island, it formed a harder shield over the loose volcanic material. Heat and water also began transforming some of the ash into palagonite tuff, a denser rock that could resist the ocean better than the original tephra. The eruption continued, on and off, until June 1967. By then, Iceland had gained more than an island. Scientists had gained something almost impossible to create deliberately: a large piece of land with a known birthday and no previous terrestrial ecosystem. Most landscapes carry a history that began long before anyone studied them. Seeds are already in the soil. Insects are already beneath the stones. Fungi, bacteria, and roots have already changed the ground. Surtsey offered a chance to watch that history begin. The opportunity was obvious almost immediately. Scientific work was coordinated while the eruption was still active. The Surtsey Research Society was founded in 1965, and Iceland declared the island a nature reserve that same year. The decision was unusual. Instead of opening the new island to tourists, settlers, or collectors, Iceland chose restraint. Researchers would be allowed to observe, measure, and sample. Everyone else would be kept away. A research shelter was built in 1966. Scientists mapped the shifting coastline, measured the volcanic material, and recorded every new form of life they could find. In the earliest years, when plants were rare, an individual plant could be marked with a wooden stake, assigned a number, and followed through flowering and seed production. That level of attention only mattered if the experiment remained clean. Imagine trying to answer a simple question. How does the first plant reach a new island? If tourists are walking across the beach, the answer becomes impossible. A seed might arrive on the wind, it might float across the ocean, or it might fall from a sock, a backpack, or the mud trapped in a boot. Once those possibilities are mixed together, the island can never be reset. Surtsey, therefore, became a laboratory without walls, but with one strict condition. Human beings could watch nature write the story. They could not hold the pen. At first, the new land looked almost incapable of supporting life. Its surface was black, unstable, and exposed to salt, wind, and violent storms. Fresh volcanic material contained little of the organic matter that ordinary soil depends on. Parts of the island were still hot. Other parts were being cut apart by waves before scientists could finish mapping them. But life did not wait for comfortable conditions. In May 1964, only months after the island appeared, the first insect was recorded. It was the beginning of a pattern. Some insects flew from Iceland or the neighboring islands. Others were pushed across the Atlantic by favorable winds. Small animals arrived on driftwood, floating grass and debris. Spiders could travel through the air on threads of silk. Not every arrival became a resident. Many died. Colonization is not the same as survival. Along the shore, marine life was also testing the new habitat. Diatoms were found on the sandy beach in August 1964. Larvae and spores moved with ocean currents, settling wherever the new coastline offered a surface they could use. The first spring after Surtsey formed, seeds and pieces of plants were already washing ashore. Some were collected and germinated in a laboratory, proving that the Atlantic could deliver living candidates to the island. Then, in the spring of 1965, researchers found the first higher plant growing at the shoreline, sea rocket. It was not a forest pioneer. It was a specialist built for beaches, able to tolerate salt, shifting sand, and poor nutrients. Sea sandwort, sea lime grass, and oyster plant followed. Their root was written into their biology. Their seeds could float, endure seawater, and become trapped high enough on the shore to germinate. Other organisms arrived by air. Spores of fungi, mosses, and lichens were light enough to cross open water. The first mosses took advantage of damp volcanic material near steam vents. Slowly, bare rock developed stains, films, and tiny patches of growth. From a distance, Surtsey was still mostly black. Up close, the experiment had already begun. Birds reached Surtsey almost as soon as land existed. Some came from colonies on nearby islands. Others stopped during migrations between the Arctic, Europe, and Africa. At first, they were visitors. Then they became engineers. Birds carried seeds in their digestive systems, on their feathers, and in nesting material. They carried insects and fragments of plants. Most importantly, seabirds moved nutrients from the ocean onto the land. The first confirmed nests were found in 1970, black guillemots, and a fulmar breeding on an island that had not existed 7 years earlier. For years, biological change remained slow. The first coastal plants held narrow patches of ground, but much of Surtsey stayed barren. Then gulls began forming a colony in the southern lava fields during the 1980s. The effect was not subtle. Every nesting season, the gulls imported food from the sea and left nutrients behind. Their droppings enriched ground that had once contained almost nothing useful to plants. Their bodies created shelter. Their nesting activity disturbed the surface. Seeds arrived with them and found conditions that previous seeds had not. After the gull colony became established, new plant species appeared more rapidly. Grasses spread. Invertebrate communities grew more complex. With more plants came more insects. With more insects came opportunities for land birds. This is ecological succession, but it is not a clean staircase where one species politely waits for another. It is a network of accidents and feedback loops. A bird carries a seed. Its waste changes the soil. A plant traps windblown material. Roots hold moisture. Insects find food and shelter. Another bird arrives because the insects are there. Each successful colonist changes the probability that the next one will survive. Around 90 bird species have now been recorded on or near Surtsey. Not all of them stayed, and not all of them bred, but together they reveal that isolation is not emptiness. The ocean and the atmosphere are constantly delivering possibilities. This is why access to Surtsey is so tightly controlled. Without a permit, visiting Surtsey or going ashore is prohibited. Diving beside the island is prohibited. Introducing animals, plants, seeds, soil, or minerals is prohibited. Waste cannot be left on or near the island. These rules are not designed to preserve Surtsey as a frozen museum exhibit. The island is supposed to change. The goal is to protect the cause of that change. A seed hidden in the tread of a boot may be almost invisible. On an ordinary island, it might mean nothing. On Surtsey, it could establish a plant years before that species would have arrived naturally. An insect inside a bag could become a predator in a community that had never encountered it. Soil caught on a tool could carry spores, microbes, or eggs. Even food scraps could alter which animals survive near the research station. The damage would not necessarily look dramatic. There would be no explosion and no oil slick. The damage would be uncertainty. Future researchers would see a species on the island and be unable to say whether it crossed the Atlantic, arrived with a bird, or stepped ashore with a person. That uncertainty could remain in the scientific record for decades. So authorized researchers work under strict controls. Equipment must be clean. Supplies must be managed carefully. Disturbance is limited. The island is not treated as a wilderness playground, but as evidence. Surtsey entered the UNESCO World Heritage List in 2008 because its value is not merely the land itself. Its value is the uninterrupted process taking place on that land. Most protected places restrict people because human activity could destroy what is already there. Surtsey restricts people because human activity could create something that should not be there yet. Protection cannot stop the greatest force acting on Surtsey. The Atlantic has been dismantling the island since the moment it appeared. At the end of the eruption, Surtsey covered about 2.7 square kilometers. By 1975, it had fallen to roughly 2.0. By 2002, only about 1.4 square kilometers remained, close to half its maximum area. The losses were greatest in the early years, when waves attacked Lustifera. In some years, several hectares disappeared. During an extreme storm in January 1990, average wave height southeast of Surtsey reached around 14 meters, with the largest waves estimated near 20. The coastline could change in a single night. Two forces have prevented Surtsey from sharing the fate of its vanished neighboring islands. The first is lava. Flows from the eruption-armored parts of the south and east, forcing waves to break against basalt instead of loose ash. The second is time. Hot water moving through volcanic ash helped convert fragile tephra into palagonite tuff. On the western side, the ocean eventually exposed a dense core that resists erosion far better than the original slopes. But resistance is not permanence. Cliffs collapse, beaches move. Habitat disappears with the coastline. As the island becomes smaller, some of the environments that allowed species to establish will vanish as well. UNESCO notes that erosion has already halved the island and may eventually remove another 2/3, leaving only its most resistant core. That means the biological experiment is being conducted on a platform that is slowly deleting itself. Species may continue to arrive even as the space available to them contracts. The number of plants could rise, reach a peak, and later decline as the island loses soil, shelter, and nesting ground. Surtsey is not simply showing how an ecosystem begins. It may also show how one retreats. From the deck of a fishing boat, Surtsey first looked like a disaster happening at sea. It became an island, then a laboratory, then a record of how wind, water, birds, and chance can turn sterile rock into living ground. Its story has lasted because of an unusual human decision to discover something and then resist the urge to enter it. That is the real reason almost no one is allowed onto Iceland's newest island. The restriction is not hiding Surtsey from the world. It is protecting the only version of the story that cannot be recreated, the version in which nature arrived by itself. One day, much of the island visible now may be gone. The waves will continue cutting into its edges, storms will move its beaches, and the surviving core will look less like new land and more like the ancient islands around it. But every uncontaminated year adds another page to a scientific record that began when a cook looked across the Atlantic and thought he saw a ship on fire. Surtsey is still changing, and for the experiment to mean anything, we have to remain outside it.